Welcome to the solubility and saturation lesson. So today we're going to be analyzing how temperature and pressure affects solubility. So again, solubility is, we've been studying this, it's the ability, to mix the solute into a solvent. The last few days we've been looking at the different intermolecular forces and we've been looking at how, substances that are, polar substances will dissolve in polar substances and so forth, and nonpolar will dissolve in nonpolar and so forth. So today what we're going to be doing is we're going to be looking at, well, how much, so say if the substances can mix, how much can you dump in, and to what degree can you dump in, and what conditions do you need in order to dissolve more and more, okay? So again, we're coming back to the word solubility again. So we're looking at today analyzing the amount of solute. So again, think of it like, the copper 2 sulfate powder being placed into water, okay, mixed up and making a solution. So I want to see how much of that copper 2 sulfate powder I can put into the water, okay, and still have it dissolve, okay, and then we're going to have certain temperature and pressure conditions as well. So anyway, before we carry on with that, when we're looking at solubility and analyzing it, you're going to find that there are going to be different units involved. So you're going to see the solubility expressed as mass per how much water you have, okay? So the mass of the solute compared to how much water is in the whole solution here. So it'll be grams per 100 grams of water. So that's one way you can write the unit for solubility. Another way is to write, the mass of the solute. So it could be grams per 100 milliliters of water. So either 100 grams of water or 100 mils of water. So that's what can change, and you'll see it both ways on various graphs. But the reason why we can report it both ways, again, we looked at this before, we were doing, parts per percentage concentration. Remember, 1 mil equals 1 gram for water, right? So you can interchange them, but just be careful when you are reporting mass, make sure to say grams, but for solubility, it's okay to report it as, grams per 100 grams of water or grams per 100 mils of water. Okay, so I've written here an example, like if we were looking at, I don't know, sodium chloride, how much sodium chloride is in this water. So if we were going to say the solubility is 5 grams per 100 grams of water, or we can say 5 grams per 100 mils of water, and this is equivalent, okay? So again, gram, 1 gram is equal to 1 milliliter when we're talking about water here. Okay, so now that hopefully you understand what solubility is, we're looking at, how much we can dump into the water today, and we know how to express solubility today. We're just going to quickly analyze just some values here. So we have a table here at 20 degrees. Okay, we're going to assume it's room pressure as well, standard pressure, and so here are the different solubilities of these different substances. So basically, it's the ability, how much solutes. Remember, it's what mass you can dump into, say, 100 grams of water. So if you had 100 mils of water or 100 grams of water, this is how much mass you can dump in, and it'll mix. Okay, this is the max that can mix. So if you're seeing here the sugar sucrose, you can dump in 204 grams into this amount of water. Where if you see calcium carbonate here, you try to dump it in that much water, it's not going to dissolve here. Calcium chloride's a little better, okay, but still sucrose here is it can really dissolve really well. So if you are looking at, I want to see a visual here. I have sodium chloride here, sodium hydroxide, and the calcium carbonate that's on the table here. So again, we have 100 mils of water here. Okay, so if I were to take all of this and dump it in here, it would mix up and dissolve. Okay, where if you have sodium hydroxide and dump it in, only this much of calcium hydroxide can dissolve in here. Okay, if you try to add more, it won't work. And then calcium carbonate, there's a little speck there to show that to a certain degree, sometimes it will dissolve, but generally they consider it zero, okay, for how soluble it is, how well it can dissolve in the solvent. We're going to be studying a lot of these curves today, where we're going to be looking at a substance like here's potassium nitrate. We're looking at its ability to, like our ability to add solid potassium nitrate to water, and we're going to look at the ability to dissolve depending on temperature and so forth, okay? But the main thing I wanted you to take from here right now is see how the solubility here in the side here, the units are grams of solute per 100 grams of water. So again, these units will, be interchanged between these two depending on who made the graph and so forth. But just keep that in mind, that that's how you have to report the solubility today. Okay, so now that we've looked at what solubility is, so again, it's the max amount of solute that you can dissolve in some solvent. So we're going to keep going with the scenario that we have sodium chloride. We're dumping it into water, which is the solvent. So sodium chloride is the solute. We're dumping it into the solvent water. And so what we can end up here with is we have three different types of solutions that can result, okay? So again, here's the first one where we have, it looks like, it just still looks like water. So I've added sodium chloride into here in the water, and I stirred it up, and it looks like I can't see the difference between the two, right? So I have sodium chloride solution here, but I could still add more, and if I mix it, it'll dissolve. Here's the next type of solution here. So again, it could look just like this picture actually. Okay, so I can actually have both of them over here. So here, this is where you've dumped in sodium chloride, you've stirred it up, and at some point, you can't add any more sodium. You could add it, but it won't mix up, okay? So this is an exaggeration. We added it so much that there's all the sodium chloride sitting at the bottom, okay? But this part here, it has sodium chloride mixed in it, but it's at its max. So that's why when we dumped in more, the sodium chloride didn't mix. So we could have a picture like this for a saturated solution where it is at its max. And so we can drop in one little crystal and it'll just float there and it won't dissolve. It'll just go to the bottom, okay? So, so yeah, that's what a saturated solution is. We have the max amount. Putting in any more doesn't dissolve it. Okay, so both of these here, we're assuming same temperature, same pressure, okay? So say this was room temperature, okay? So here I could have added more, it will dissolve. Here, even if I add another crystal, it won't dissolve. Okay, so here, what's happening is, oh, why does it look like the unsaturated solution? So what I did here was I added, some heat to it. So let's say I, put it on a hot plate, or I don't know, put it over a Bunsen burner here. So we added heat, okay? So when we did that, we increased the temperature, and so now what happened was, so this the salt that was piled up here that wasn't mixing has now dissolved. Okay, so now it's dissolved and it's in the solution here because I added heat. So again, if you think about it, if you think about like grade 8 particle theory, those particles of sodium hydroxide or sodium chloride are moving faster, farther apart. The water is moving fast and so forth, so that it's actually helping the sodium chloride crystals to dissolve in the water. Okay, where when it was at room temperature, it would hit its max and then it couldn't dissolve anymore. Okay, but we have a lot more energy in this beaker here, so that's why now the crystals have dissolved. Okay, so again, this is an exaggeration. We would have to add a lot of heat here to get this to dissolve. So, but anyway, so we're at supersaturation here. So that means that now, compared to what it would have been at saturated, in the saturated solution, I can now dissolve all this extra sodium chloride that I normally wouldn't have been able to do if it was at the room temperature. Okay, so again, make an assumption that these two are at room temperature, and then this one is a lot hotter. Okay, so it's greater than room temperature for this one here. Okay, because I put it on a hot plate or took a Bunsen burner to it and so forth. Okay, so now this third one here is considered to be supersaturated because it's holding way more than it's capable of at the room temperature. Okay, so what will happen in this case here is that, because like again we were doing our little test to see what would happen if I added a crystal. So if I added a crystal here, nothing would happen. It would just dissolve. If I added a crystal, it would just float. But for supersaturation, if you add, like, so it could look like this where it's all mixed in and you add a crystal, and what will happen is a precipitate will form. Okay, so basically a solid will form. Okay, where you had everything was dissolved and then it's already supersaturated. So when you drop that next crystal in, it'll just form a basis. Like, it's what happens is that one crystal's there, and then all the other sodium chlorides are in the solution will start building on that one crystal and make a huge crystal. Okay, I'm going to show you a video of this actually happening here, just because we can't do this at school right now. So we have, so again, a supersaturated solution, if you want to see the definition, is it's an unstable solution. So basically, even like, once you heat it up, it all mixes, and then you have it sitting on the table cooling down. Even if I knock it with my finger or just like bonk the desk that it's on, it can actually cause it to completely crystallize, like not completely, but like to crystallize like this, to precipitate out. Okay. But what I'm going to show you here, like if you look at these ones here, this is an example where they added a seed crystal. So they added one little tiny crystal, and you see it slowly, the precipitate happening here. Okay, but I'll show you a video right now. I have the links here too if you wanted to look at them after, but yes, I'm going to make a video of a video. Okay, so here it is.
Okay, just really quick, I'm going to add one tiny seed crystal. I'm not sure if you can see on the tip of that scopula there. Right at the tip, we're going to add that to my supersaturated solution of sodium acetate. And we will see it go from a supersaturated state to a saturated state in just a few seconds. Isn't that cool? So we see that the sodium and acetate ions recognize the crystalline structure of that seed crystal I just added, and they add to it, and we form one big crystal. And when I tilt this to the side, you can see it looks like a big chunk of ice, doesn't it? So now we're back. There's a little bit of water in there. You might be able to see it, but we're back to our saturated state right now. So we've gone from supersaturated to saturated in just a couple of seconds.
Again, in that video, he started with a supersaturated solution of, I think it was sodium acetate, he said. Yeah, so I think it's the same as this picture here. And so basically he would have, dissolved tons of sodium acetate into water, heated it up so that, a maximum, like more than a maximum amount of sodium acetate could dissolve in the water. Okay, and then when we started watching the video, you saw him putting in one little crystal of the sodium acetate, and then it slowly started to crystallize like that. Okay, so you should now understand the difference between unsaturated, saturated, and supersaturated. Okay, so unsaturated, you still have, more space in here. You can add more sodium chloride. Saturated is when you've maxed out. You can't, even if you add some extra stuff in there, it won't dissolve. Okay. And then when we manipulate the situation where we add heat and we allow the extra stuff to dissolve, then we have something that's super saturated, right? So we have more than what this amount of water could handle, but we manipulated it by adding heat. So now those particles are moving fast, and they're bumping into each other, and they're causing the salt particles, the sodium chloride particles, to dissolve in here, okay, and stay in solution. So we manipulated the situation. So now we have a super saturated solution. So way more sodium chloride is dissolved in this water than what it can normally handle at room temperature, or whatever the temperature was. Okay, so we changed the temperature and caused it to be super saturated. So when we added the crystal here, so what happened was that we went from super saturated back to the saturated, where it caused the crystals to come out. And then if you actually did touch this container, you would feel heat coming off as well, because now it's going back to the saturated state here, where it's taking out all the excess salt that it can't handle. Okay. But now we will move on to solubility curves. So we're going to start looking at these graphs of different substances, and sometimes they're going to be on the same, like several substances will be on the same graph, and it's about being able to read the graph and just tell me um, your understanding of the saturation of the substance. Okay. All right. So the solubility curves, we're going to look at varying the temperature right now. We'll look at pressure and solubility in a second, but we're just going to adjust the temperature, and we're going to look at the ability of a solute to dissolve in water, depending on the temperature and also depending on how much solute you do add. Okay. So each point along the curve, okay, so if you do have, so you're going to have these curves here. The curve actually represents the saturated part. Okay, so that's where the maximum amount of solute can dissolve at that certain temperature. And so it'll tell you, oh, 70 grams can dissolve at, 42 degrees. 100 grams can dissolve at 55 degrees, etc. Okay, all right, so let's go through and see if you can read the graph. So example 1 here, we have 90 degrees of potassium nitrate. So here's this graph here in 100 mils of water. So what is the degree of saturation at these following temperatures here? Okay, so what I want you to do here is I want you to start with the 70 degrees. So I'll circle it in red here. Okay, so that's the first one. So maybe I'll even call it 1. All right, so 70 degrees. Here it is, 70 degrees. Okay, so this is temperature 1. So I want you to go up until you get to 90 grams. Okay, so 90 grams of potassium nitrate. So we're going to go up, up, up. Okay, so here is 90 right here. So I should almost just draw the 90 gram line here. Okay, so that's 90 grams. Okay, so we're going up. This is 70 degrees Celsius. Okay, so here is the point that 90 grams is at when it's 70 degrees. So if you're looking here, in this region here, this is all unsaturated. So basically, if you have a temperature of 70 degrees and you dump in 90 grams of potassium nitrate, it will dissolve and you still have space to add even more. Okay, so you would say here that this solution is unsaturated because it's in the unsaturated zone. Okay, so that point that you made here is in the unsaturated zone. Okay, so again, it's below the line here, below the curve. Okay, so when it's below, it's unsaturated. At the line, it's saturated. Above it is supersaturated. Okay, so do the same with the next one. So we'll call this question 2 or part 2. So we have 50 degrees here now. So let's go find 50 degrees. Okay, here it is. I'll call that part 2. All right, so we're going to go up and see where we are when we hit the 90 gram line here. Okay, so we hit 90 grams right on the curve here. Okay, so when you're right on the curve, you are considered to be a saturated solution. Okay, so at a temperature of 50 degrees, if I dump in 90 grams of potassium nitrate, it will be saturated. So basically, 90 grams is the max that you can dump into 100 grams of water at 50 degrees. Okay, and the last one, we'll make it purple or light blue, Okay, all right, so here we go, 10 degrees. Okay, so 10 degrees, here it is. Okay, this is part 3 here. Okay, so I'm gonna go up until I hit the 90 gram line, and there it is. Okay, so there's that point. So at 10 degrees, if I dump in 90 grams of potassium nitrate into 100 mils of water, I'm going to have way too much stuff in there. So I'm going to be super saturated, okay? Okay, so yeah, I know it has both, so you could just kind of just call it super saturated because I know like once we, add that extra crystal, it'll become saturated again and so forth, okay? But just before we add that last crystal here, if we, have it at this temperature here, yeah, and if we can get this dissolved in here, then it will be super saturated. So given certain conditions, so given the temperature, given the mass of the solute, can you determine if, what kind of saturation we have? Do we have an unsaturated solution, a saturated solution, or a supersaturated solution? Okay, example 2. So describe each of the following solutions. Again, so we're describing them as supersaturated, saturated, unsaturated. So what we're doing here is, here are the conditions. So we have 100 grams of potassium nitrate. So we could use this graph, or we can use the one down here. Just maybe we'll use this one. In 100 mils of water. So we have 100 mils, okay, and it doesn't say water, but it is in this case here, yeah, in water. And it's at 40 degrees. So I want you to, with those conditions, we have 100 grams of potassium nitrate and 40 degrees Celsius. What is the degree of saturation? All right, so I'm just gonna circle this one in red. Okay, all right, so we have 40 degrees Celsius. So let's go find 40 degrees. There it is. So I'm just going to call this question 1. And we have 100 grams of potassium nitrate. So we're going to go to 100 grams here. And I have 40 degrees. So I'm just going to go up here. Okay, and we're just trying to figure out. There it is, right? So if you don't need to draw these dots in, you don't have to. But if you can just find where it's 100 grams and it's 40 degrees. So even if you're a mathy, if you want to think of it as like 40 degrees Celsius and 100 grams, where's that point on this graph? That's what you're doing, okay? So you're taking your temperature and you're taking your solubility, I guess, okay? All right, so you're finding the point. There it is, okay? And then we look for potassium nitrate. Okay, because this says potassium nitrate, so here's potassium nitrate. Here's the curve for potassium nitrate. It's this one that goes like this, okay? So, so if we take a look at where that point is compared to where the saturated line, remember this curve here is the saturated line? See how it's above? So you would say this is supersaturated. Okay, so if I ask you for the degree of saturation, that's what I want. I want you to tell me supersaturated, saturated, or unsaturated. Okay, so for the next one here, we have 50 grams of potassium chloride in 200 milliliters of water at 0 degrees Celsius, okay? So this one here we have to be careful with. We're just going to write it over here. So we have question number 2. We have 50 grams of potassium chloride in 200 milliliters of water, okay? So if you look at the graph, all the results are in grams per 100 milliliters of water. Okay, so we have 200 here. So we just have to, be careful with questions like this and just get it converted down to 100 milliliters of water. Okay, so if you're looking here, and again, you're a little bit tired, you can't make this conversion, so you went from 200 to 100. What did you divide by? 2. Okay, so you need to divide 50 by 2, and you'll get 25 grams. Okay, so that makes the conversion so that now that's what you're looking for. Instead of 50 grams, you're looking for 25 grams of potassium chloride. Okay, so here, I'll circle this here. Okay, so we're looking at 0 degrees, which is here. And so this is question 2, 0 degrees. And we're going up to 25 grams of potassium chloride. So here is 20, 22, 24, 26, like that. So right in the middle here is 25. Okay, so we've gone up, and that's the mass. So now we're looking for the potassium chloride, which is right here. Okay, so all the labels on this graph are found underneath the curve. Okay, so remember, so this line here that's purple, but this line here represents where it's saturated, right? So where is this dot? See how it's below the curve here? So that means number 2 is unsaturated. Okay, because it's found below the curve, and below is unsaturated. All right, okay, move on to the next one, number 5. Okay, so just watch out for that. If it's not the same units, it has to be per 100 grams or 100 mils of water. Okay, so here's this one. We have 50 grams of ammonium chloride. There it is right here. Okay, and 50 grams in 100 mils, so that one's okay, we don't need to convert, at 50 degrees Celsius. So let's go find 50 degrees Celsius. There it is. So we'll call this question 3. All right, so what you're going to do here is you're going to go up to the 50 grams marker here. So we have 50 degrees Celsius and 50 grams. So I'm just going to put the dots in so you can kind of follow along. And then here's 50 grams. Okay, so here is the dot. Okay, so I'm looking at ammonium chloride. So this line here that goes like this is the ammonium chloride curve. And remember the dot, so the dot is right on the curve. So remember when you're right on the curve, you're saturated. So we'll write that here, saturated. Okay. Okay, so for the fourth one here, we have 30 grams of ammonium bicarbonate or ammonium hydrogen carbonate in 300 milliliters of water. So again, watch out here at 15 degrees Celsius. Okay, so before we start looking at the graph, we just need to make our adjustment here and make some conversions here. So we have 300 grams of ammonium bicarbonate, okay, and in 300 milliliters of water. Okay, so just make the adjustment so that it's in 100 milliliters of water instead. Okay, so work with that value so you can read that off the graph. So again, all you're doing here is you're looking at, okay, what did you do? What do you need to do to go from 300 to 100? Well, you need to divide the values by 3, okay, and then you get 10 grams of ammonium carbonate, okay, or bicarbonate, sorry. So, so that's what you're going to use on the graph here. So we are at a temperature of 15 degrees Celsius. So there it is in here. And then we're going to go up till we hit 10. Okay, so 15 degrees is right here. Okay, so that's 15. Okay, and we'll call this 4, question 4. So we're going to go up until we hit the 10 degrees here. Okay, and there's not 10 degrees, sorry, 10 grams. Okay, so there it is. And so then now we're looking for the ammonium bicarbonate. There it is. It's just a short little graph here. Oops. Okay, there it is. And so we're finding that this point that's right there is below the ammonium bicarbonate graph. So we are unsaturated when we're below the saturated line. And I said the labels were all under the curves, but this one here is above it, just I guess because it was getting a little bit messy here with all the intersections here. Anyway, so if you were wondering why does the curve stop here for that one, stop here, and then these other ones kind of keep going, you can think of it as like, these are in solution, and if we're increasing the temperature, you're going to end up like boiling it off. So yeah, we can't, add more heat, like we can't add 40 degrees because now we'll be in a different state and so forth. So yeah, we're just looking at that solid being able to stay in the liquid. We don't want to start analyzing the gases here. Okay, so we'll look at the gases in a second, but yeah, just in case you were just wondering why it stopped here. One more examples, and we'll start looking at the gases and how pressure affects solubility. With this one here, so we have potassium nitrate again. I want you now, so we've been looking at, connecting the temperature and the mass together. So now what we need to do here is I need you to find how many grams of potassium nitrate are required to create a 100 milliliter saturated solution at 40 degrees, okay? So we have some conditions here, and we need to figure out how much potassium nitrate that we need to mass out, put into this 100 mils of water here so that it'll become a saturated solution, okay? All right, so again, let's look at, so we're looking at this potassium nitrate curve. We know on the curve is saturated, above it's supersaturated, underneath it is unsaturated. So at 40 degrees here, we are going to go up. So here's 40 degrees. We're going to go up till we hit the curve here. Okay, so there it is, and then we'll go across. So it's about here. Okay, so so this is the mass. So remember, this is the mass that you need to add, okay, because this is the solubility, to 100 milliliters of water or 100 grams of water at 40 degrees for it to be on the saturated curve line here, okay? So we're going to approximate. So let's see here, it's about, just say 68 grams of potassium nitrate, okay? So So yeah, so 40 degrees has to be saturated. Okay, so this is the mass that you would need here. Okay, all right, here's example 4. So how many grams of potassium nitrate per 100 mils of water would be crystallized from a saturated solution as the temperature drops from um, 70 to 30 degrees? Okay, so with potassium nitrate here, we're going to look at this graph again. So we're looking at, going from 70 to 30 degrees here. So here, whoops, it's 70, okay, down to 30. So we're going from 70 down to 30 in temperature. Okay, so we have a saturated solution of it. So if we look up here and go up till we hit the line here, okay, so we have a saturated solution. Okay, so since it's saturated, okay, so at 70 degrees, we have a mass of 140 grams. Okay, so we have a saturated solution, 140 grams. So that means there's 140 grams because we're at 70 degrees. So now what happens when we drop it to 30? Okay, 30 degrees. So we're going to go up and see where that is. It looks like it's just below here. So we'll go with what, 49 grams. So what we have here is we started at 70 degrees, we had a certain solution, and we put in 140 grams of potassium nitrate, okay? So now we let the temperature cool, and so now we're at 30 degrees. So what's happening here is that because now it's cooled, you're still at 140 degrees, but you're here. The point is right there, okay? So now we're at 30 degrees, so the point is there. So now the solution has become super saturated. Okay, so so when it's super saturated, so you saw that in the video there. We add that little crystal, or even if we knock the side of the bottle and let it cool, you will find that the solid will come out of solution and crystallize, okay? And so they want to know in this problem how much is actually going to come out of solution. So if you take a look here at 30 degrees, we can hold 49 grams, okay? So so the max that it can hold at 30 degrees is 49 grams. So if, again, it was at 70, and then, but the temperature drops. So now it's only capable of holding 49 grams. So how much is going to come out of solution? What you're going to do is you're going to subtract these values here, and you're going to determine that this is how much will crystallize in the beaker or whatever container you have. Okay, so again, you had a solution that was at 70 degrees. It held 140 grams of solute in it, and it was saturated. Okay, but then we took that same solution and we just allowed the temperature to drop. So we're looking at the graph, and we can only hold 49 grams. Okay, so approximately 49 grams of the solute potassium nitrate in solution when it's 30 degrees. Okay, so that means the extra 91 grams that you stuffed into there and heated it up, that's going to come out of solution and just crystallize here. Okay, all right, so that's pretty much all the different questions that you'll see today when it comes to the solubility curves and temperature. Okay, so now that we've looked at solid being dissolved into water at certain temperatures and so forth, so we're going to start analyzing what's happening when we have gases and when we adjust the temperature as well. Okay, so if you look at this example here, so the solubility of gases decreases as temperature rises. So if we look at oxygen here, it's dissolved in water. So at 0 degrees, it contains 0.014 grams per liter of water. Okay, so again, as temperature increases, you can think of it as from a particle theory perspective, where those molecules of water and oxygen are in the solution and they're gaining energy, so they're starting to vibrate and move around and so forth, and to the point where it'll the oxygen will just come out of the water. Okay, so if we're looking at 0 degrees, you have this amount here, but If you look at 35 degrees, we only have 0.007. So basically, you can hold twice as much oxygen when the temperature is at 0 degrees compared to 35 degrees. That's what naturally happens in the summer. The surface of the water will be warmer. So, but there are issues with industrial pollution where the companies are dumping water back into the rivers. But if it's not the right temperature, if it's a different temperature from what the river temperature is, it's considered to be thermal pollution. So again, it can affect the ecosystem there. Again, it can affect the dissolved oxygen content, and if the fish are having to go too deep into the water so they can stay in oxygenated water, then their ability to find food is limited and so forth. So again, it can affect the survivability of a lot of the different organisms in the ecosystem. Okay, so to finish today, we're going to look at how pressure affects solubility. Okay, but in general, pressure doesn't affect solids and liquids just because they can't be compressed. But pressure can significantly affect gases because you can compress them. Okay, and they take. So like here's an example picture here. So we have a container. We have a lid on it here. And so say we have, it could be, like this is the liquid water and this is the oxygen, okay? So here's this amount of pressure. So this is what we're going to see, without a lot of pressure here, the two substances will not be together, okay? But when we increase the pressure, what's going to happen is that the gas at the top will mix with, the water or the gas at the bottom here. Okay, so with that increased pressure, you'll find that it can improve the solubility. So that's how we look at it. Okay, so it's all about mixing things together. So so if we're looking at it with increasing pressure, we can find that we can increase the solubility. So for example, if this was oxygen and water, we can get more oxygen dissolving and mixing in with the water here when there's increased pressure. So, with this, so the more pressure you have, the greater the solubility. So, okay, so the solubility of a gas in a liquid, so this is like oxygen and water, increases as the pressure increases. Okay, so here's an example. We have a soft drink here. So if we're looking at it, it hasn't been opened yet. So the fizziness within the pop here is created from the carbon dioxide. So this is a carbonated drink. So basically, it's under high pressure when they create it at the factory, and so you'll find that their carbon dioxide molecules are dissolved in the solution here, the liquid here. Okay, all right. And so what happens when you open up the container here, you're going to find that and because the pressure inside the bottle here of like the concentration of carbon dioxide is way greater than what you have in the atmosphere. So once you open it up, the carbon dioxide will escape out of the pop and then go into the air. So that's why you hear that sound, okay, the fizzing sound. So you're hearing that carbon dioxide leaving and so forth. So again, when it's in the bottle, it's pressurized, so the carbon dioxide stays a certain concentration. But when you open it, now it's being released out into the atmosphere. So if you leave this, this glass or even this bottle open for a while, you'll find that it'll become flat. People say the pop became flat because the carbon dioxide escaped from the solution. Okay, so what you'll also find is if you take a bottle of pop that's been chilled in the fridge versus a bottle of pop that's just been sitting, in your pantry, and drink the warm bottle. So if you try them both, you'll find that the one that's been in the fridge just it seems like it's got more poppiness to it, right? So, and the reason for that as well is if remember we looked at here. So as you increase the temperature, the gas will kind of leave the liquid, right? So the colder it is, the better the gas will stay soluble within the liquid. So when you have pop that's chilled, you're going to find that the carbon dioxide will be mixed better with the pop. where, so you have this little gap of air here, right? So if it's if it's warm, you're going to find it's going to have a tougher time staying dissolved, and then yeah, it'll be kind of coming out of solution here. Okay, so it's just better when you have it chilled. Okay, so since we're talking about pop, I just wanted to show you a video that connects kind of our solubility here with what we're doing today with pressure and temperature, and then also connect with the intermolecular forces. It's another video within a video, so here we go.
Trick, you'll be able to take any bottle of soda and pour out an instant slushy on command. Now, if you don't believe what you're seeing, that's okay, but it is real, and in this project, you'll discover the insanely easy secret to making an instant soda slushy. For this project, grab a bottle of room temperature soda and start shaking it violently. We want as much pressure to build up inside as we can get. Now I've done this with these 500 milliliter bottles and set them in the freezer for 3 hours and 15 minutes. This is the point when they're colder than freezing, but not actually frozen. Now you can show your friends that it's just a normal soda, but watch what happens if we simply release the pressure, tighten the cap, and turn it upside down. In just 3 seconds, the entire bottle is turned to an icy soda slush.
Okay, if you wanted to watch the rest of the video, here's a link to it that you can go to. So basically, what is happening there when you're taking the pop, freezing it for a certain amount of time, and then opening it, allowing some of the fizz to come out, and then closing it, and then shaking it up. Okay, so why is it freezing over, and so forth. So I want you to, again, we're looking at carbon dioxide here, and so again, when it's cold, it's dissolved in water, but when we open it, we're releasing some of the carbon dioxide out, okay, out of solution here. So so say that this bottle is what we did, we froze and so forth. So some of the carbon dioxide is coming out of solution here. So basically, we've left this this drink in the freezer for a while of time. So in general, when you leave, ice, like liquid water, in the freezer, you'll find that it becomes ice, right? And so we know how ice forms. We talked about H bonding and so forth, and how you end up with those hexagonal structures. And so with the because of H bonding and so forth. So when you open the water bottle here, some of the CO2, okay, the carbon dioxide leaves the solution. So basically, when you had the carbon dioxide in the pop here, it almost in a way disrupted the H bonding, okay, so that the pop couldn't freeze. So again, if you leave the pop in there for a really long time, then the pop will freeze. But just for that short period of time that we're freezing, having the other molecules in the water, so let's just say it's carbon dioxide and sugar and water and so forth, it was disrupting the H bonding from happening. So once we release some of the CO2 by opening up the cap, what's happening now is because there's less carbon dioxide, then the H bonding can happen, and so that's why we're going from liquid to solid pretty quick. Okay, so it's a neat little trick here, just that makes us connect with the intermolecular forces plus the whole idea of solubility that we're studying today. So again, just check with your parents and see if they'll let you do this, but it should be safe enough. But I just don't want you to be making a mess in your freezer and so forth. But it's kind of a nice little trick that you can try at home. Okay, so we'll get to our last example here, and then you can kind of review the notes and complete the checkpoint. So this example has to do with scuba diving and so forth. So basically, we're going to look at scuba diver here. They're at the top of the water, so there's a certain amount. So at the top, 0 meters depth here, we have a certain pressure, say 1 atmosphere on the lungs. Okay, so now if you were to descend into the water, so have you ever gone in and swam, you will notice that you feel this pressure on your lungs when you're, like, even if your head's above water but your body's under the water, you'll find that it's a little harder to breathe and so forth because the water is creating pressure on your lungs and on your body. So so as you go deeper and deeper into the water, you'll find that the pressure does increase. So say so if we say we go down 10 meters here, the pressure is now 2 atmospheres. Okay, Now you have that increased pressure now that you're deeper in the water. So we've looked at how pressure affects the solubility of gases, right? So again, we were looking at a gas here and a liquid here. So when the pressure wasn't as great, you found that they weren't mixing as well. But when you increase the pressure, now that gas can dissolve into the liquid. So what's going to happen here is when you go and descend into the water into greater depths, you're going to have an increased pressure on your body. And so you're breathing in from your oxygen tank some oxygen, some nitrogen's in there as well. And what you're going to find is that as you go deeper, the pressure is greater, so the nitrogen will actually move from your lungs into your bloodstream. Okay, so and then from there, the procedure is to slowly go back up to the surface when you do a deep dive. So you go up and then you stay at a certain depth, and you go up again a little bit higher, and then you go up again, and so that's the procedure to follow, because then the nitrogen can slowly come out of your blood and back into your lungs, where when you get up to the surface, you can breathe it out. Okay, so what happens here if you um, you know, go from a deep dive here and then just suddenly go right up to the top, you're going to find that the nitrogen doesn't have time to come out of your blood back into your lungs. What will happen instead is that it'll come out in your blood as a gas, or it could be in your tissues. Like, so if the blood was in your near the tissues and so forth, it might become a gas in your tissues and so forth. So anyway, this whole process, what happens is that you end up getting decompression sickness because of that, because you have this nitrogen where it's not supposed to be in your body and so forth. So that's why they say that you have to, when you're coming, when you do a deep dive, you have to come back up slowly. So you float back up, stay at that level, then float back up to another level, and slowly back up to the top. So a lot of stuff today. I just wanted to add a lot of the stuff with the pressure and the and so forth, and just because it's quite interesting. So like, just because some of you might drink pop and you're just wondering what's going on when you open it and so forth, and the slushy thing is awesome. I discovered it actually by accident because I like drinking things cold, and I forgot about my drink one day, and I meant to keep it in there for like 5 minutes, and I left it in there for an hour. And when I opened it, I just had this surprise where it turned into slush. So it was awesome. And anyway, and then some of you, might want to go or have tried scuba diving and have wondered why, they probably told you you'll get the bends. So, you have to go back up slowly, but now you actually know the chemical understanding of it, I guess, and so forth. So anyway, just make sure that you understand solubility of gases, and but the big ones here, can you answer questions like this on the solubility curves, determining where it's saturated, supersaturated, or unsaturated, and so forth. Okay, all right, and so then when you're good to go, try the checkpoint.